Hello, I'm Alex Algitz. This is my 3-minute paper on a robust machine learning framework to predict CYP450 inhibition. Essentially, CYP450s are 450 to 500 amino acid proteins that are really relevant to drugs. They're kind of like OATPs, in that way that they're mid-size in the liver, relevant to drugs, that kind of thing. Um, so machine learning methods have been used to classify ligands for these as inhibitors or not. Previous methods have included QSAR, XGBoost, graph networks, and more traditional methods. XGBoost was the best performing of these models. Authors chose to use a majority voting model. So here's kind of the framework of their model. They process the chemical and the protein, dock those, have different features generated, and then from those generated features, filter them down and plug them into the majority voting model. So pre-molecular docking, they include a cavity analysis using Cavity Plus. This looks at potential binding sites on the protein. They use PyMol to calculate the surface area, either the solvent or the ligand can access. Smaller ones generally perform better. They're simpler. Um, they also use protein ligand interaction features in a novel fashion for the CYP450s. This is like the first time they're kind of used. So they use AutoDock VNet to dock proteins and ligands, and then protein ligand extended connectivity fingerprints, PLEC, to get like a machine learning feature out of that. They also use recursive feature elimination to refine the model and avoid overfitting. Just gets rid of the least important features for model generation. The authors kind of found that sometimes it had like a little bit of positive performance as the amount of features or the amount of bits or descriptors went down. But as you can kind of see here in the figure, it kind of just tapers off after a certain number of features included. So they use a majority voting model. They have 3 bagging and 2 boosting ensemble learning methods. Just 3 of them have to agree to classify a ligand is the meat of that part. So the results of this study, they're interesting. They're not super revolutionary though. Compared to the gold standard XGBoost model, their results are all right. Some of the isoforms are more accurate than the ones used in the XGBoost paper. Others are not. The authors kind of choose to focus more on the inclusion of RFE to refine the model, avoid overfitting. That could have possibly taken place in the XGBoost model. Each isoform ends up having a different optimal performer. And as I mentioned before, the smaller bonding cavities perform better.